Hello, everybody. It's great to see you here. Sorry, I'm going to be looking below the camera today. I'm staying with my sister and her family, so I'm in a different location. But it's great to be here with you all. Thank you all for joining me today. Today we're going to talk about the subject of climate change, and um, we're going to talk about fossil fuels. Fossil fuels are a big, important subject related to climate change and pollution. And climate change is, in my opinion, the biggest, most important subject that we're facing on this planet today. Climate change, in according to the science and according to my opinion also, is that climate change is pushing us rapidly towards uninhabitability, uh, pushing this planet towards uninhabitability. That's a big deal. If we're all not going to be able to live in our environment on our planet in the next 2 or 3 decades, perhaps sooner, that's a big deal. And there's, people have their opinions about this. People also have knowledge about this. I'm going to try and share with you today some knowledge and back it up with data and graphs and information. Now, when people talk about climate change, I come back to what Marcus Aurelius said, and I'm not sure if I'll remember the exact quote, but something like, the opinion of 10,000 people is worth nothing if none of them know anything about the subject. Well, today I'm going to try to share with you some knowledge, some information about the subject. So it's been a little bit of a last minute frantic dash to get to the right place to log into StreamYard from this new location. So I'm just pulling up my files now. This is an important piece of information here. The latest information that is readily available to us shows us how in the US we get our energy. And there is petroleum in there. That's basically oil, crude oil. We have natural gas. We have coal. Those three combined, if we do a little bit of quick math, is something like 82% um, fossil fuels. And the other energy, the place where we get our other energy, is some from nuclear power, and some from renewable. So 9% nuclear power, 9% renewable, that adds up to 18%, which leaves 82% of our energy in the US comes from the burning of fossil fuels. This is another graph that shows basically the same thing. Some people think that renewable energy is doing really, really well in this country. Well, if you look at the green slither at the top of all of those other colors, that's renewable energy in this country. And crude oil is the mauve or dark red. Natural gas is the lighter blue. And coal is actually not doing as well as it has done in the past. It's actually decreasing, but fossil fuel consumption overall is increasing. As you can see from the graph, it's never been higher. So I'm going to tell a story about fossil fuels, where they come from, why they're important, why we need to know all about fossil fuels. And the story of fossil fuels starts 4.6 billion years ago with the formation of our planet. So 4.6 billion years ago, our planet was it was very hot. It was not like our planet today. The atmosphere was largely carbon dioxide. It was mostly carbon dioxide. The Earth's natural atmospheric state is an atmosphere of carbon dioxide. Now, you probably know this, but carbon dioxide is toxic to humans. So if we had have been attempting to land and live on our planet at that time, for the first billion years, we would not have been able to. Actually, for the first 2 billion years, as I will explain in a little bit, we would have been breathing in poison. Now, I have experienced what it's like to have carbon dioxide poisoning before. It wasn't deliberate. They tell you that if you've got to be careful not to put plastic bags over your head, because if you do, you'll be breathing in the carbon dioxide. Any oxygen that's in there, you'll breathe in the oxygen. Your lungs will breathe out carbon dioxide, and you will be breathing in a bag of carbon dioxide. Well, I didn't do that deliberately one time. What I did was I went to a Halloween party wearing a mask that covered my face so much that I was not getting in the oxygen that I needed. And so I experienced what it's like to breathe in a carbon dioxide atmosphere. And very quickly you start to feel lightheaded, you start to get a headache, you start to realize that you're suffocating. That's what it would have been like if we had been living on the planet at that time. We would have died very quickly. That's not the only problem with carbon dioxide. One of the other problems with carbon dioxide is that it acts like a thick blanket around our planet. It traps in heat and causes a warming or a greenhouse effect. So the full process of global warming, of warming the planet due to carbon dioxide, is a little bit more involved than some people realize. The overview is that, like with a greenhouse, here's a greenhouse image, the sunlight can come into the greenhouse, but then the heat of the sunlight cannot escape from the greenhouse. It gets trapped inside the greenhouse. Well, in reality, what is happening is, to our planet, the sunlight is coming in, all of the light, not just visible light, a wide range of the electromagnetic spectrum, that's all coming through the atmosphere, and it warms up the Earth. And that Earth then, and the ocean, it emits the heat energy up into the atmosphere. The atmosphere warms, every single bit of the atmosphere warms. The atoms in the atmosphere capture that heat, and then they re-emit it. But when they re-emit the heat, they're not just emitting it upwards into space, they're emitting it downwards to the planet. And the more carbon dioxide there is in the atmosphere to absorb the heat and then re-emit it in all directions, the hotter the atmosphere gets. So that's kind of a complicated way of saying greenhouse effect or global warming. Now, that was going on 4.6 billion years ago when our planet first formed. So the temperature of the planet at that time was about 230 degrees Celsius, which is about 446 degrees Fahrenheit. Think about that temperature on this planet. At that time, the temperature was about 446 degrees Fahrenheit. That would not have been fun. That is the natural state of our planet. And we can actually get a glimpse of what it would be like to live on a planet like that, or to try to live on a planet like that, if we look at Venus. Venus has a very thick heat trapping atmosphere, and it's closer to the sun than the Earth is, and it's a lot hotter than this planet is. It's too hot for us to land on Venus and survive for more than a few minutes. Now, Mercury is closer to the sun than the Earth, but Mercury is actually a little bit cooler. So Mercury is the closest planet to the sun out of all the planets, but it's not quite as hot as Venus. The order goes Mercury, Venus, Earth. And that is because Mercury does not have a very thick atmosphere. It's a very tenuous, weak atmosphere, doesn't hold in the heat. But Venus, the next planet out away from the sun, does have the atmosphere, so it traps in the heat, and it's the hottest planet in the solar system. Well, the Earth was a bit like that 4.6 billion years ago. After about a billion years, so we're looking at about 3.5 billion years ago, then something special happened, and we had evolved on this planet life. Now that's actually an artificially intelligently generated AI image of early life, and that early life, some of it was photosynthetic. So we're looking at simple single-celled organisms there, plant-like, algae-like life evolved in warm oceans on this planet. Now, interestingly enough, there's just been a release in the news, science news, about what they discovered from material that they recovered from the NASA mission that went to the planet Bennu. I don't know if I'm saying that name right, but they visited a year or two ago. They visited the planet Bennu, and they captured on that planet. They sort of crashed into it, and they captured material from, not planet, from the asteroid. And a lot of material went into the capturing device of the space probe, and then they shipped that, they brought that asteroid material back to Earth, and they recovered it, and it came back down. It came back down on a parachute, and we captured that material, and scientists have been studying it, and they've just released a news article and paper about some of the molecules that they discovered on that asteroid. And what they discovered on that asteroid was something like, honestly, I don't have the article in front of me, but it's something like 19 out of 23 of the amino acids that we have in our bodies that we use to create the proteins within us. Well, it turns out that amino acids are common throughout definitely the solar system. We have found amino acids in meteorites, in material that has come, fallen down through our atmosphere, hit our planet. We've discovered it in cometary and asteroid material. Amino acids are common in space, in these asteroids, in these comets, in these meteors, and that's what they discovered on Bennu as well. The same is true of those four building blocks of DNA. Those letters, like from the movie Gattaca, the G, the A, the T, the C, those molecules, they also found all four of them on this asteroid. Now, that doesn't mean that there's life on the asteroid. What it means is, when you in this universe have a jumble of different elements, then those elements naturally, through electromagnetic forces, fall together, come together. Well, it's electromagnetic, it's electric attraction, positive attracts negative. They naturally come together to form more and more complex structures. It's no mystery to us why protons and electrons come together to form atoms. It's the positive of the proton, it's the negative of the electron coming together to form atoms. And then it's no mystery what the chemistry of how different atoms come together, because again of positives and negatives, electric charges coming together to form larger molecules. This happens. This is a natural process. And this happens throughout our solar system and probably throughout the universe. And this new piece of news that's come out about the molecules on the asteroid show us that the building blocks of life, those complex organic molecules, amino acids, and the base molecules of DNA, they're abundant naturally throughout our solar system and very probably throughout the universe. That's very important because a lot of people will tell you, a lot of people that know nothing about science will tell you it doesn't make sense that life just evolved out of a random mix of chemicals. Well, the science tells us that they're wrong. It makes perfect sense, and it's actually been proved to be the case that this happens. So we have on our ancient world, on the Earth, after the Earth has cooled sufficiently that through natural radiation of heat out into space, what happens is the lava has cooled enough, the magma has cooled enough that a crust formed around the planet. That continents started to form because the atmosphere had cooled enough that it started to rain, and rain started to fill up into oceans. To start with, it was too hot for water to condense out of the ocean and form liquid water. To start with, the only water molecules on the planet Earth used to be in the form of water vapor, gases. They'd evaporated basically into the atmosphere. Well, then after 1 billion years, the Earth had cooled sufficiently that it had rained enough that shallow oceans had formed. And in those shallow oceans, as I just showed you, something looking like that formed. And this, let's see, here is an image of a fossil of some of those early life forms. This is a fossil called a stromatolite, which I think in Australia there are quite a lot of these. And these are the oldest fossils on this planet. And these fossils are 3.5 billion years old. We can date them with science very, very simply. And these are 3.5 billion year old fossils. And when we analyze these fossils, we see that they are a type of cyanobacteria. They are mats of cyanobacteria, life on this planet after 1 billion years of cooling. And they were photosynthetic mats of simple organisms that were photosynthetic. Now, the fact that they're photosynthetic is very important because they evolved in this very, very hot climate that was a carbon dioxide atmosphere. Photosynthetic organisms, they take the light or energy from the sun, and that's the photo part of photosynthetic, and they synthesize, they make using light and also using carbon dioxide from the air. They make sugars for themselves. They make molecules out of carbon, organic molecules that they can then make their bodies out of. That's what photosynthesis is. That's what plants do. They take some water from their surroundings, they take carbon dioxide from the air, they take energy from the sun and photosynthesize sugars like glucose that they make into their bodies. That's what plants do. And these organisms, 3.5 billion years ago, they were doing that. They were taking carbon dioxide out of the air and making their carbon or organic moleculed bodies. Now, a waste product for them in that process is oxygen, carbon dioxide, CO2. They take the C, they reject the O2, and the O2, the oxygen, goes out into the atmosphere. Now, to start with, the rocks on the planet Earth, they were pretty basic. They had not reacted. They were not oxides. They had not reacted with any oxygen in the atmosphere. If there was iron, for example, present in these rocks, it was pure iron. It was shiny. It was metallic. The surface of the planet at that time, the rocks would have looked very shiny, metallic. But then, due to the photosynthesis happening all around our planet, that oxygen was released, and oxygen is very reactive, and it started to react with the elements in the surface on the surface of the Earth, and you get from you transition from something that looks like this, like basic iron, into something that looks more like this, iron oxide. Now, I've been in iron oxide mines before, and it is this reddish brown substance. It's basically rust. These rocks are basically rust, and you can see here that they're sedimentary rocks that they've built up in layers due to the erosion and probably motion of water. But the point that I'm trying to make here is, while all of this was going on, there was not oxygen actually in the atmosphere that would be available to breathe. We can go back, if we could go back 3.5 billion years, we wouldn't have been able to breathe. The oxygen was still reacting. The oxygen that was being released through photosynthetic processes was not accumulating in the atmosphere. It was reacting with rocks. So you had these cyanobacteria, these ancient algae-like organisms that were releasing the oxygen, taking carbon dioxide out of the air, releasing the oxygen, but the oxygen was just reacting with the rocks. But then we get to a stage about 2.5 billion years ago, when all of the rocks had finished reacting with oxygen. There were no just pure elemental elements lying around on the surface of the Earth. Everything had reacted with oxygen. And then 2.5 billion years ago, you started to get oxygen, free oxygen, starting to build up in the atmosphere. And then you have a very noticeable decrease in carbon dioxide. The carbon dioxide comes down, the oxygen goes up, and you get an atmosphere that starts to build up oxygen about 2.5 billion years ago. Now, when that happened, that was wonderful, because then we started to get evolving the first oxygen breathing organisms. Those organisms were actually organisms like comb jellies, sea anemone type organisms, sponges that were in the shallow oceans of the time. And then that whole evolution thing happens, and you get many millions, billions of years of evolution. And we're going to skip a lot of that because it's not relevant to fossil fuels. What is relevant to fossil fuels is that, let's see, I'm just going to jump back to my notes because I'm doing a lot of this from memory, just checking where we are. It was about 350 million years ago that we had surrounding a large area of this planet. There were lots of tropical swamps full of plants, enormously rich in plant life with these tropical swamps. And these swamps were made of plants that were photosynthetic. And these plants were sinking, they were dying, they were sinking into the swampy, marshy layers like this, and sediments were building up on top of them, and then more dead plants were dying and pushing down on top of them, and layer after layer after layer for millions of years of these tropical swamps were being pushed down deeper and deeper into the ground. And over millions of years of this process happening, with more sediment and more dead plant matter, more sediment, more dead plant matter for millions upon millions of years, all of these layers pushing down on top from above squeezes the deeper layers, puts them under pressure. By squeezing things, not only are you putting them under pressure, you're putting them under, you're increasing the temperature, and you're having chemical transformations occur where these dead tropical swamp plants are transitioning, are transforming into scenes of coal. Now, coal is rich in organic molecules, in hydrocarbons, in dead plants, the molecules of dead plants. These molecules are full of carbon. We know that when we burn something, though the burnt things look kind of black, and that's carbon. Coal contains a lot of carbon. And what this whole process, the reason I'm talking about this whole process, is so that we can really understand what coal is and what it represents and how it got there. Coal represents an overall process that happened over hundreds of millions of years, where photosynthetic organisms, where plants took out carbon dioxide from the atmosphere. They released in place of the carbon dioxide oxygen. And this carbon, or we could say the carbon dioxide, the carbon was all pushed down under the ground, into the ground, safely out of our atmosphere. For hundreds of thousands of years, the carbon dioxide has been being removed and pushed down into the ground for hundreds of millions of years in the form of coal. When we burn coal, when we dig up that coal, and when we burn coal, what we're doing, burning is adding oxygen. What we're doing is we're adding oxygen to the carbon that's in those molecules. We're releasing carbon dioxide. We are releasing back into the atmosphere all of the carbon dioxide that it took photosynthetic organisms hundreds of millions of years to take out. We are turning back the atmosphere rapidly. This is a very quick process of us digging up all of the coal and burning it. We are turning back the atmosphere into the atmosphere of millions of years ago. We have already, through the burning of fossil fuels like coal, we have already taken our atmosphere back to how it was millions of years ago, before humans even existed on this planet. This is having enormous impacts on life on this planet, because life adapts slowly and evolves according to what the environment is like. We're changing the environment much, much quicker. In just the Industrial Revolution started about 250 years ago. That's when we really started to burn coal and other fossil fuels. We dig it up out of the ground very rapidly and we burn it. And we use the energy that's inside it. And this is just the science. I'm not even talking about the morality of this yet. But there's another fossil fuel that's of great importance to us, and that is oil. So where does this oil come from? What are the consequences of burning oil? Well, oil is also a fossil fuel, and think of the word fossil. It forms in a very similar way that to coal. Coal forms from plants in tropical swampy areas. Oil forms not from, well, some of it may be plants, from plankton in oceans. Now, there's two types of plankton. There's plant-like plankton that we call phytoplankton, and then there's animal-like plankton, which we call zooplankton. And the zooplankton being animal, very, very, very tiny animal-like organisms, they tend to eat the phytoplankton. Now, the phytoplankton, the plant-like plankton, little microscopic, tiny plant-like organisms throughout our oceans, they're photosynthetic, so they absorb huge amounts of carbon dioxide out of the atmosphere. And they formed also hundreds of millions of years ago. I'm just whoops, I'm just jumping back to my notes here. The oil that we use today was, a lot of it was started to be formed 250 million years ago, not quite as old, some of it as the coal, but it's also hundreds of millions of years old. And what happened was, the whole process is, we've got phytoplankton drawing out lots of carbon dioxide from the atmosphere into the plant-like little beings, organisms in the oceans. You've got the animals, the zooplankton, eating the phytoplankton, and the carbon dioxide is being taken out of the atmosphere, and the carbon is going into the bodies of all of those organisms, all of the plankton. And when that plankton dies and it sinks down like misty, sort of dead snow down to the ocean floor, it builds up on the ocean floor. And sediments and more dead stuff, and sediments and more dead stuff. And that happens for hundreds of millions of years. And the effect is that carbon is being removed from the atmosphere and pushed deep down under layers and layers and layers of, eventually, rock. And we can drill up that rock today if it's still underneath the ocean. We use oil rigs that look a little bit like that. If we do it on areas of land which used to be under the ocean, then we have things like that. They're called nodding donkeys. But we can drill up that oil, and we can burn that, and that is where oil comes from. Now, when we burn that oil, we are releasing back into the atmosphere. We're releasing the carbon dioxide that used to be in the atmosphere over the hundreds of millions of years that the oil was forming, that the plankton was dying. And so when we collectively burn the coal and the oil, and also the natural gas, which basically accumulates, it's like the gases that accumulate when coal and oil form, that's where the natural gas comes from. When we burn those three fossil fuels, what we're doing is we're releasing all of the carbon dioxide that it took hundreds of millions of years for photosynthetic organisms to take out of the atmosphere. We're just putting that carbon dioxide back into the atmosphere. Now, a lot of people may not see initially a problem with that. There are small problems, I say small problems associated with coal and oil. Those include things like acid rain, sulfur dioxide, just typical normal pollution. We've got oil spills where birds and other aquatic organisms and coastal organisms are killed and badly damaged. Ecosystems are destroyed because of oil spills, which seem to happen quite a lot. They've happened every year or two. There are oil spills, tankers rupturing and oil spilling out into the oceans and polluting all around the world. That's been going on certainly my entire life. Those are relatively small problems compared to the big problem of changing our atmosphere back to how it used to be hundreds of millions of years ago. When we throw this carbon dioxide molecule back into the atmosphere, not only is it toxic, it is also a greenhouse gas. It's heating up the planet. So this obviously is a big problem. And it's extraordinary today that people in governments around the world, including you might find it in the news in the US, that government officials are being put into positions of power who openly say that climate change isn't a thing. Well, science tells us that climate change, global warming, is a thing. This is a graph from actually a few years ago, and it's actually got worse than this since this graph was made. But this graph goes back hundreds of thousands of years, with the present day on the right-hand side at the 0, and hundreds of thousands of years going backwards through time to the left. And there are two graphs, two curves, two lines on this graph. The orange line, that is, or orange or dark brown, that line represents the changes in concentration in parts per million of carbon dioxide in the atmosphere throughout the last nearly 100,000 years. And you can see that there's natural fluctuation up and down and up and down and up and down. And that natural fluctuation happens for a number of different reasons, mostly tectonic, volcanic reasons. And in response to that, you can see when we look at the temperature fluctuations that have occurred on this planet, which is the blue line, that the temperature fluctuations very closely match the fluctuations of carbon dioxide in the atmosphere. It basically shows that carbon dioxide is a greenhouse gas that causes, when there's more of it in the atmosphere, the temperature of the planet to go up. When there's less of it, the temperature to go down. These two graphs of the temperature has been slightly moved higher than the carbon dioxide graph, just so that we can see the correlation a bit more clearly. And this is the reality of the science of what happens when the carbon dioxide fluctuates in our atmosphere. You can see that towards the right-hand side, we've just come out of a trough or a dip in both the concentration of carbon dioxide in the atmosphere and also the temperature. That was an ice age. And you can see that ice age started to happen about 100,000 years ago. And the temperature of the planet got colder and colder and colder, and many of the oceans and a lot of the land was covered in ice. And it was only actually about 12,000 years that we came out of this ice age, because of naturally increasing concentrations of carbon dioxide in the atmosphere. But there's something that's not clearly different that's just happened on the far right. If you look at that graph on the far right, the line, the orange or the dark orange or brown line, it just rockets straight up, higher, to a much higher level than it has been in the entire 800,000 years of the rest of that graph. Why has that happened? That has happened because of the burning of fossil fuels. And the burning of fossil fuels has caused the concentration in parts per million of carbon dioxide that is in the atmosphere to go up from, in the region of, well, based on this graph, if I'm just eyeballing it, about 270 parts per million, all the way up to, well, it's actually higher than that now. The concentration of carbon dioxide in the atmosphere is now about 423 parts per million in the atmosphere. So this graph is out of date by a few years. But I would like you to look at the right-hand side of that graph and think, what is the corresponding temperature increase likely to be just on eyeballing the rest of that graph? And if we just make a prediction based on simple eyeballing of that graph, an estimate for the temperature increase that's corresponding to the increase in carbon dioxide that we've already caused is over 10 degrees Celsius, which is approximately 20 degrees Fahrenheit. We have committed ourselves with the burning of carbon dioxide, with the releasing of carbon dioxide due to the burning of fossil fuels. We've already committed ourselves to an increase in temperature on this planet of about 20 degrees Fahrenheit. That's a global average temperature of 20 degrees Fahrenheit. I would like you to think about how hot it has been in the last summer where you live, and imagine the temperature being 20 degrees Celsius, sorry, 10 degrees Celsius hotter than that where you live, or 20 degrees Fahrenheit hotter than that where you live. That's what we've already caused, and the temperature is just catching up to what we've already caused. We've put the blankets on, and that's causing the temperature to increase. Even if we don't add any more blankets, we've still got, our planet is still going to keep getting warmer and warmer and warmer until it catches up to what we've already caused. That carbon dioxide is a reckless and, in my opinion, because morality is opinion based, in my opinion, an immoral release of carbon dioxide and other greenhouse gases into the atmosphere. This is an immoral thing that we're doing. And who is it benefiting? It is benefiting people who make money out of fossil fuels, which is rich people around the planet who own the fossil fuels, the fossil fuel industry. My nephew's just arrived outside, which is why I've just waved at him. So this is big and this is serious, and I'm going to talk some more about this. That's the graph we looked at. This graph goes back about 400,000 years, so it's zoomed in a little bit more detail, and you can see there even more clearly that the temperature fluctuations caused by the CO2 concentrations are very closely matched. And there's a third line, and that third graph, the blue one at the bottom, is sea level. And you can see that there is a very, very clear correlation between between the CO2 concentration, the global temperature, and the sea level. When we increase the concentration of CO2, then we increase the temperature and the sea level increases. And we are due now, with the increasing temperature that we're experiencing right now, and it's continuing to rise every year, breaking records every year, we're going to experience a sea level rise associated with that, because you increase the temperature of the planet and the ice in the Arctic and the Antarctic regions melt, and that melted water goes into the oceans rise. And if you were to think about, again, eyeballing this, we're looking at something like 100 to 200 feet of sea level rise around the planet. That's enough to completely change the planet's appearance. Maps are going to change. Coastal regions are going to go underwater. Now, a lot of people will tell you that this is all just, well, some people will tell you climate change is fake news invented by China. I mean, there's not, people say nonsense out there, But this is real science, and we can look at real science like this. This is called the Keeling curve. The Keeling curve shows the actual increase in carbon dioxide. This is simple to measure, and it's been going up since about 1960 when this pattern was discovered. And we've known that the concentration of carbon dioxide has been going up since that time. It's something like 80 years that we've known that the carbon dioxide levels have been increasing. And you can see in this Keeling curve, even though we've known that this has been happening and we've known that there's a temperature increase associated with this, politicians have not been doing anything about it. And that's because politicians are supported by the fossil fuel industry. We have known that this is occurring, but this is not easy knowledge. This requires people to actually think a little bit, to learn a little bit. And a lot of people don't like thinking. A lot of people don't like learning. If you're listening to me now on this podcast, you're doing a really great job, because you're allowing yourselves to go through the mental effort of learning something. Well, a lot of people are not like you. A lot of people are not like that. And therefore they can't get the knowledge that's needed to understand that climate change is real. And if we look at the actual temperature increases that have occurred since, in red on the right hand side, we started burning fossil fuels, you can see that the temperature is going up. It is actually verifiably going up to temperatures that we have not experienced in well, millions of years. And that temperature increase is accelerating. It's not even a straight line. That's accelerating up. Now this graph is a little bit out of date. I've not had time to look up the most recent ones, but we, you know, when this was all discovered, there were people around the world that said, well, maybe we should try and keep the temperature increase less than 1.5 degrees Celsius, because if we could keep it less than 1.5 degrees Celsius, or about 2.5 degrees Fahrenheit, then maybe we'd be able to cope with that. Maybe it wouldn't be catastrophic. And there were agreements around the world that were made, hundreds of countries coming together to try and make these agreements. And but certain politicians and certain parties and certain countries who are heavily supported by the fossil fuel industry have basically said, no, it's not even real. It's not even real science. We don't need to worry about this particular subject. And there's been disinformation given about this for many years. And unfortunately, in our world today, disinformation is winning. When you look at around the world, which politicians are being elected, the politicians that are trying to combat climate change, those are the politicians who are not being elected, because there's not enough knowledge about climate change for people to realize how serious this is. What we're looking at over time is verifiably, scientifically, for wise, knowledgeable people, we can see that the temperature is continuing to increase in very, very clear ways. In these images that I'm showing you, the red shows where temperature is increasing, and there are little tiny little pockets around the world where the temperature has not been increasing due to, I don't know, mountainous regions or geographic locations, weather patterns. But we have a big problem. And some people say, well, when COVID happened, then everything went back to normal, right? We stopped releasing all that carbon dioxide and we reset. Well, this graph shows that there was a little dip in the emissions of carbon dioxide, but not by much, because people are still at home using electricity, and So that's simply not true, that there was this big dip in carbon dioxide emissions. And, you know, we're back now to how we were before, with the carbon dioxide increasing. So what can we do about this? I've got 3 minutes of this. I've got 2 minutes left. What can I tell you that is hopeful? Well, I can't tell you that we're going to save the planet, because we're not. We've initiated the next mass extinction on this planet. It's official. It's the Anthropocene mass extinction, Holocene mass extinction. It's got 2 different names. We're doing it. What's going to happen is that the population of humanity is going to collapse. And we're seeing around the world now, with wildfires, with floods, increasing and increasing. Imagine that increasing 100-fold, 1,000-fold. That's where we're moving into. People are going to die, homes are going to be lost, climate migration. We're moving towards apocalyptic situations, and the people who are making money out of it don't care. And the people who are making money out of it are spreading such disinformation that people don't care that they're dying. They don't know that they're dying, and those who know don't care. We're in a pretty terrible situation. What is the positive part of any of this? The positive part of this is that people like me, who have relationships, friendships with advanced non-human entities, we're building little communities of wise, kind people who care about this sort of stuff. We're building little communities that are going to survive through this, in very carefully crafted communities that are being supported and joined by non-human entities. They've been giving us this message for many decades, not just through me, but through many people. They're my friends, and I invite you to join our community. This evening, we're having an event where we're actually, you know, I'm not even going to go into it, but we're connecting with them. We connect with them 2 or 3 times every year, every week, and in a very significant way. And I invite you to join us. And can I, before I end, yes, there it is. If you would like to join us, then here's the website. You can join that for free, and you can learn more, you can watch more videos, and you can join our community. It's a collaboration of beings of light. You can join us if you would like to. I've gone a little bit over, so I'm going to say goodbye. Peace, love, and happiness to all of you. Take care. Goodbye for now.